reaction before ketone. Can you explain that though? Okay, so there are two reasons. All right, and for this reason, aldehyde and certain type of ketone can react with wide range of nucleophile. Look right there. These are the number of reactions you're going to learn. How many? Can you count? This is the reaction in this chapter you will learn. Is it scary? Ooh, very scary. Ooh. Okay, there are 12 reactions total that you will learn in this chapter, and we use that in predicting product and synthesis. Okay, now it's your options, it's your decision to treat those 12 reactions as 12 separate reactions, or you want to find the common features of those reactions and group them together. Which one easier for you? I'll leave it up to you to decide. Okay, a lot of them have common features. I'm gonna show you. Okay, today I'm gonna go through right here. This is today, right there. Oxygen nucleophile, sulfur nucleophile, and nitrogen nucleophile. That's what we're gonna focus on today. Okay, all right. How many reactions right here? 1, 2, 3, 4, 5, 6, 7. There's a 7 right here. You can boil them down to 2 reactions. Let me show you how. Okay, first thing first, put your pen down. I'm going to have you grab your pen 4 times today. We're going to focus on looking at the pattern, recognizing the patterns. Can we do that? I'm going to tell you when to pick up the pen and write out the mechanism, okay, or predicting the product. That's all you have to do today. We're going to focus 100%, use everything you have in your brain, focus on looking at the pattern, what they have in common. Okay, let me show you. So all this reaction, we're gonna put into 2 categories. Now, put 2 types of reaction. One, we call this acidic condition. What does acidic condition mean? Reaction that run under use acid. Basic. Does it make sense? What's the opposite of acidic condition? The basic, those 2, just those 2, and they have their own mechanism. Okay, all right, first thing first, when you add an acid, can you guess what's happening first when you add an acid like hydrochloric acid? What we call that mechanistic step when you add an acid? What happened? Pronation, right? So the ketone or aldehyde would be pronated. You activate it basically from more stable needs neutral, stable to become unstable. Can you see that though? Okay, that's why this step requires strong acid. For example, like sulfuric acid. Okay, we use a lot of sulfuric acid in this chapter. Okay, all right, one become reactive. Now we add a nucleophile. So nucleophile undergo, what do we call this step right here? Answer the question. What do we call this step? Nucleophilic attack. Do you know that? Have you heard that term? Have you heard that term? We call this nucleophilic attack. You gotta know this one. Okay, all right, the last one we call this what? Depronation, just reverse of an acid. We have pronation, and they follow by depronation. Protons in, protons out. We call this acid catalyzed reaction. Acid going in and acid coming out. Does it get consumed? The catalyst, right? All right. Under basic condition, basic like hydroxide. Imagine like hydroxide. This guy has strong nucleophile already. So first thing first, they nucleophilic attack. See that? Okay. Followed by depronation. Pronation on this guy. All right. Here's the patterns. One more time, walk me through it. If you use acidic condition to do reaction on ketone and aldehyde, what's happening first? Tell me. Pronation followed by nucleophilic attack and depronation. If you use a basic condition, what's happening first? Depronation and pronation. Okay. Let me show you the first reaction. Let's see if it follows this. Okay. All right, here we go. So first one we call hydration. Start with the term hydration. What does hydration mean? Stay hydrated. What does it mean? Adding water. Okay. So when add water, so onto aldehyde to ketone, mostly this is the side reaction. When you put like aldehyde ketone in a solution, if the solution have water, they have this reaction. Okay. And mostly they go backwards. It's a side reaction. All right, let's check out the mechanism. Okay, under acidic condition or under basic condition? acidic condition. What's happening first? Pronation. If you haven't opened your mouth yet, I'm looking at you. Start with pronation. Next step is nucleophilic attack. Okay, so carbocation, right? That carbon is slightly positive due to the resonance effect. Okay, so you can attack right there on the carbocation. Not carbon, the carbonyl carbon. All right, when you get to this point, do you recognize that this guy looks like a hydronium ion? Are you seeing what I'm seeing? Okay, what's the pKa of hydronium ion? Negative. Is it acidic or is it a strong acid or weak acid? Hydronium ion. Strong acid, negative 1.7. That's why the last step is depronation. It won't survive in a solution, a strong acid, right? Can you see the patterns? Okay, try one more time. What condition are we doing reaction in? Basic condition. Basic condition, for example, sodium hydroxide. Sodium hydroxide is already a strong nucleophile. First step is nucleophilic attack. Okay? That's a strong base. Can you see that? You get a base. Base underwater, like sodium hydroxide in water. Pick up a proton, pronation. Just reverse of the acid. Let's summarize. Okay? Look at the whole thing. So we have this is basic condition, this is acidic condition. They have that pattern, and all of them under basic condition, under acidic condition, they have that patterns. There might be some variation, you'll see it in the next reaction, but it's just the same thing. Pronation, nucleophilic attack, depronation. Proton syn, nucleophilic attack, proton cell. It goes like that. Okay. All right. Here's a common mistakes. Do not do this on exam. If I say that, one or two of you will do it for some reason. Okay. So focus, really focus on this. Okay. You gotta be able to recognize that this doesn't make sense. Okay. But let me point out for you first. Start with the basic condition. This is under basic condition. Right? Imagine a sodium hydroxide solution. What would happen to the sodium hydroxide solution if you add, let's say, sulfuric acid, like pour sulfuric acid into it? We call neutralization, right? My point is, an acid and a base can or cannot coexist. Cannot. They kill each other right away. We call neutralization. Can we agree on that? That's a basic principle of acid-base reaction. Acid and base cannot coexist. Well, the weak one, sure, right? But the strong one cannot coexist. You pour sodium hydroxide to sulfuric acid, pour hydrochloric acid to sodium hydroxide solution, they kill each other right away. So under basic condition, take a look. Nucleophilic attack, you get that pronation. You cannot use hydronium ion. Does that make sense? One, we didn't add hydronium ion. Did we have hydronium ion in here? No, you cannot use that. You cannot use a reagent that you don't add. Number two, this is a basic solution, strong base solution right here. You cannot use hydronium ion because even if you add, they kill each other right away. Does that make sense? Okay, so do not do that on exam. And under acidic condition, you cannot use what? A base. It's the same principle. Okay, do not use what's it right there, hydroxide attack, like depronation. You cannot use that. One, we didn't add sodium hydroxide. Two, acid and a base cannot coexist. If you understand what I just said, say I. Okay, any question on that? I would rather you ask me right now than later. People on Zoom, any question on that? Under acidic condition, you cannot use. Open your mouth. You cannot use base. Under basic condition, you cannot use an acid. That's it. Okay? All right. Make sure we clear on that. Let's start with the next reaction. Okay? We call this acetyl formation. You don't have to memorize the name. Okay. Oh, just watch. Nothing to do. Nothing to do. Put your pen down. Acidic condition or basic condition? This is acidic condition. Okay, let me explain first what's going on in here. Okay, the reaction occur between aldehyde ketone and an alcohol. Okay, how many alcohol molecules attack the ketone or aldehyde? 2. Okay, you're gonna end up. I'm gonna go back one slide. You're gonna end up with like 2 water molecules. 2 water molecules. Can you see that though? Just very similar. Okay, you end up with 2 alcohol molecules making ether basically. All right, but anyway, so we call this acetal. Okay, so 2 alcohol molecules attack carbonyl carbon. We go through an intermediate called hemiacetal. Hemi means half, like half water, half alcohol. This comes from water, this comes from alcohol. Okay, half water, half alcohol. Again, if you don't know it, it's fine. You don't really care about it. We focus on the mechanism. This is under acidic condition. The acidic condition, the acid that we use is anything familiar? At least you know sulfuric acid, right? Strong acid. We have another one, para-toluene sulfonic acid. Treat them just like that. Can you treat them the same way? That's a sulfonic acid group. That's a sulfonic acid group. It's the same thing. Can you see that? It produces, it's a strong acid, produce at least 1 extra proton, 1 proton. Okay, all right. So when you dump this into water, the identity of an acid is not them, is whatever solvent come pick up, that guy right there. If you use alcohol, it's a protonated alcohol. Let me explain this first. If you add sulfuric acid into water, so the whole water, like 1 drop sulfuric acid, what would happen to that sulfuric acid? Think. Basic acid-base chemistry. You know the answer. Add a drop of sulfuric acid to water. As soon as it hit the water, what happened? Have you heard the term dissociate? Okay. You know sulfuric acid is strong or weak acid? Strong. You learn from Gen Chem that strong acid dissociate completely, 100%. Have you heard those terms? Okay, so as soon as sulfuric acid hit water, surface of water, it dissociates right away. It dissociates right away. Can you see that? This is the real identity of an acid, not that. Not sulfuric acid, not para-toluene sulfonic acid. It's that guy. Am I clear on that? It only depends on how much of this you add. Sure, if you use concentrated sulfuric acid, yes, you use sulfuric acid in the solution when you draw the mechanism. If you use dilute sulfuric acid, small amount of acid, that's the identity of an acid. Okay, we call this leveling effect. You can look it up, what it means. All right, so all right, I'm going to use this protonated alcohol as the source of the acid. Okay, all right, watch closely. Let's see if you can see the patterns. It's the same thing. Don't touch your pen either. Just eyes up. Okay. This is under acidic condition. Answer the question. What's happening at the first step? Protonation. Here's a protonation. Notice that I didn't use sulfuric acid. Can you see that? This is a protonated alcohol. Okay, I'm going to go back 1 slide. Alcohol is used as a solvent. This guy pick up the acids come from these 2, either one of these 2. This guy pick up the proton and become that. You know? So I'm going to use the protonated alcohol, whatever alcohol you put in there. All right, protonation, the first step. All right, when this guy becomes activated, what's the next step? What's the next step? Nucleophilic attack. Good job. Okay. Now, do you recognize that this look like a hydronium ion? Right there. Hydronium ion is a strong or weak acid? Strong acid. What's going to happen after? Deprotonation. Can you see the patterns? Okay. All right. This is half alcohol, half water. We call hemiacetal. This is halfway done. All right, from hemiacetal, we're going to go all the way to acetal. Who has to leave? The OH group, right? The water side. This guy got to leave. Are you following on that? Okay. Now, some of you know alcohol. Is alcohol a good leaving group? No, you cannot just make it leave like chlorine, bromine. You cannot do that. When it go back to Argo 1, some of you might remember. Let's refresh it. When you want to make an alcohol leave, what needs to happen to it first? Protonation first, right? First step, protonation. Can you see the patterns? This is under acidic condition. First step is protonation. Same thing there. Okay. All right. Here's a slight twist. Okay. What's the next step they're supposed to have? Nucleophilic attack. All right. So it's supposed to be nucleophilic attack like that. But now you learn. This is an SN2 reaction. You learned before. Can nucleophilic attack, like backside attack, occur like that in that center? Tell me why not? Backside attack. What slowed down the rate of backside attack? The steric hindrance. Can you see this is quaternary carbon? You cannot do that. See that? So SN2 rate is too slow. We just assume that it doesn't exist. Well, but the reaction have to go further, right? We can't do nucleophilic attack here. What do we do? This is what we do. Okay? So this is steric hindrance. Too high steric hindrance. You cannot do that. We kick out the leaving group right there, the OH group right there, OH2 right now look like water, by using a lone pair on oxygen of an alcohol. Kick them out. See that? Now, look what happened. This is important. When this happened, you go back to this guy. That's a carbonyl carbon, right? This allows nucleophilic attack. Here's the reason why. One more time. What's the hybridization state of this carbon? sp2. What's the geometry of sp2? Trigonal planar. Trigonal planar, like carbocation ion, is flat. Remember that? If you remember SN1 reaction, carbocation ion, there's a front side attack, some back side attack. You end up with racemic mixture. Remember that? Steric hindrance is not an issue. Nucleophilic attack happened right there. Do you understand that? Now, last step. Look right here. What do you think you need to do? Depronation. Look at overall. Nucleophilic attack. Oh no. Pronation, nucleophilic attack, depronation. Pronation, nucleophilic attack, depronation. Can you see the patterns? It's freaking the same thing. 7 reaction today is that. Are you going to memorize them as 7 separate reaction or just 2 reaction, acidic condition and basic condition? You got options. That's up to you. Okay. Question on here. I'm about to have you draw the arrow. Okay, but any question on here? Not yet. I got one more slide before I let you do it. Any question on here? Make sure it's clear. I would rather you ask me right now than going to the exam, walk out and say, hey, I just learned something new. Dude, that's not the right way to do. Question.
Like negative H2O right after the first.
This means that water leaves. Minus H2O, like a math, it's like equation, right? So, okay. All right. Just a little bit more about this reaction, so you understand everything about it. Okay. The reactant and the product. This is aldehyde ketone, and this is the acetal. Okay. They are in equilibrium, which means that they can go forward, they can go reverse until it reaches equilibrium. Okay. Reaction never stops. You know that, right? You learn that equilibrium, how it works. Okay. So, to get to the, let's say you want an acetal as a product. This is equilibrium. If you want acetal, you want equilibrium to go which way? To the right, to that way. How do you control an equilibrium? That guy's name. What's that guy's name? Le Chatelier's. Remember that? Okay. If you really want to go to the right, there are 2 things you can do. Add a lot of what? Reactant to drive it forward, or remove the product to drive equilibrium forward. Does that make sense? Okay. So look at this guy right there. Okay, to drive equilibrium to the right, you just add a bunch of reactant. Here's how they do it. They just use ethanol as a solvent. Does that make sense? That's the maximum amount of the reactant you can add. Just use it as a solvent. Drive it forward. Okay, and at the same time, this is in practice they can remove water at the same time, but we're not going to get there. So my point is, from this slide, just tell you one thing. When you do acetal formation, we use alcohol as a solvent. So don't freak out if you don't see any reactant. This guy's a reactant and a solvent at the same time. Does that make sense to you? Okay. Now what? Here's what we're gonna do. Okay. Go look at the handout. You have the reaction scheme, the whole reaction equilibrium. All you do, draw the arrows. I'll leave you to that. Same patterns. Pronation, nucleophilic attack, depronation. Now let's try if you can do it on your own. Eyes up. Okay. You tell me what to do. First step, pronation. Okay. Followed by nucleophilic attack. Now, what do you use to do nucleophilic attack? It's in there, but like when you draw the mechanism on your own, what do you use? Ethanol. Look at the product. That's an ethanol, two ethanol molecules. Can you see that? Ethanol attack. Okay, so we pick up ethanol and then attack that. Next step is depronation. There's a strong acid right there. There's a strong acid there. Look like a hydronium ion. So depronation. Halfway done. Hemiacetal. All right, hemiacetal. Move forward. Next step is pronation. All right. If you have to draw a mechanism on your own, look at right here. Who get pronated? The alcohol side or the water side? The water. Here's you think about it. If you pronate an alcohol, what happened? I mean, it's valid. You just go backward. See that? They are in equilibrium, so it's correct. You can do that too. But mechanism-wise, it doesn't get you to the product. And depends on how you control the equilibrium. Go forward, go reverse. Okay? So if you want to make, so this guy has to leave. If you want to make this guy leave, you pronate them. That's a look better leaving group. You know? Much better leaving group. pK 16, go down to pK negative 1.7. Much better leaving group. All right, next step. What happened? You're going to be able to explain that. There's a nucleophilic attack. There's a pronation, depronation. What's happening at this step? We call loss of leaving group. Do not do that. You know, right? You cannot do that. So we do loss of leaving group. Use a lone pair on the alcohol. That ether, whatever you want to call it. Okay? And then our sp2 carbon, now this is flat, trigonal planar. So nucleophilic attack can occur right there. And followed by depronation. It's long, but it's not complicated. Do you agree? It's long, but it's not complicated. They all have the same patterns. Okay? How many? Eyes up. How many alcohol molecules react with aldehyde ketone? Most of you are like lost. Do you understand my question? How many alcohol molecules react with aldehyde ketone? 2. Everyone understand what I said? There are two alcohol molecules on ketone in the product, right? In acetal. So 2 alcohols can attack ketone or attack carbonyl carbon. All right? And the mechanism just like that. Can you draw this mechanism at home? Not today, at home. You gotta try. Watch. Let me point out. Hold on. Can you see that this alcohol has 2 alcohol in it? Do you think anything will be different? Can you see 2 alcohol molecules? Let's say Ronald, 2 alcohol functional groups. There and there. They both can attack. One at a time. One at a time. See that? Now, there's 3 steps to hemiacetal. You wanna guess what's happening at the 3 step? First thing, pronation followed by nucleophilic attack, and that's the 3 step. Can you see that? Now, but how come though from hemiacetal to acetal? Why there are 4 steps, not 3 now? What happened? That's a loss of leaving group. That's a loss of leaving group right there. See that? So 1, 2, 3, 4 steps. You think you can do that? Dude, you better. If I put this on exam, you're gonna be able to do it. It's long, but it's not complicated. Make sense? Okay. Now we call this guy cyclic acetal. It's an acetal, but in a cyclic form, like a circle. Okay. We use cyclic acetal as a protecting group in synthesis. Let me show you. All right. Forward, this is what we call protection. Going forward, so this is acetal formation, making acetal. All right. So we can control the equilibrium by removing water. Use this diol as a solvent. Okay. All right. Write down real quick. This compound is called ethylene glycol. Can you spell ethylene? And then glycol, Glycol. Ethylene glycol. That's just how we communicate. So I don't want to say like that molecules. When I say ethylene glycol, it's that one. It's named ethylene glycol because it's made from, it can be made from ethylene, like alkene, 2-carbon alkene. Okay. All right, look what happened. Once you add ethylene glycol to aldehyde ketone, we're making an ether bond. That's an ether bond, you know? And ether is quite inert, which means it doesn't do a lot of reaction. Okay, so ether bond is inert or stable under basic condition. Because when you add an acid, you can remove it under acidic condition. We'll talk about mechanism later. Okay, so we use ethylene glycol to protect aldehyde or ketone. Okay, and this guy is stable under basic condition. Yeah, this is pronate. This is a protection and then deprotection. Now, let me explain this one more time. Okay, so the aldehyde ketone and the cyclic acetal, they are in equilibrium. Are you following me on that? They are in equilibrium. Okay, so let me explain this way. When you do protection going forward, water is coming out. So there's water as a product. I'll say one more time. When ethylene glycol attack, water, that's water right there, you get protonated twice, okay? It's coming off. So water is a part of the product. Are you following on that? And if you understand Le Chatelier's principle, water is a product. If you add water to this side, what happened? They go backward. When you want to remove the ethylene glycol, you add a lot of water. See that? Flood them out. It's in equilibrium. When you want to go forward, we use ethylene glycol as a solvent, drive equilibrium forward. Okay. When you want to go backward, add water, because water right here, flood this guy out. Equilibrium goes backward. Use acid as catalyst, same thing. That's how we control the equilibrium. Okay. We use ethylene glycol in a situation like this. Look, that's something familiar. Do you know how to convert an alkene to an alkane? Come on, you're gonna know this reaction. We call this hydrogenation. Remember that? You add hydrogen gas and what else? Platinum, palladium, nickel. Okay, those are 3 metals you can use. On exam, do not add all of them together. They're expensive. Pick just one. Platinum really expensive. You know platinum very expensive. Is it platinum that's more expensive than gold? Platinum, right? Okay. Yeah. So no one uses platinum. So all right. If you use a straight hydrogenation, there's a possibility that a ketone or aldehyde get reduced too. See that? In this case, you do protection first. So we protect aldehyde ketone by using ethylene glycol, acetal formation, put a hat on it, see that? And then do functionalization, do whatever you want. And last step is add water, flood this guy out, deprotection. That does make sense. Okay, let's do one more time. If you try to write this down, you don't have to, it's in the handout. You should use the handout. Otherwise, you're gonna keep writing, like not listening and just keep writing. Look at the next one. Do you know how to convert an ester to an alcohol? Do you know how to convert an ester to an alcohol? We use lithium aluminum hydride. Hydride attack twice. That's why you have from that carbon right there, you get 2 hydrogen on it. Hydride attack twice. Okay, but now lithium aluminum hydride also reactive toward aldehyde and ketone. This guy get reduced too. Can you see that though? In a situation like this, it's called for protecting of the aldehyde or ketone. Okay, same thing. Add ethylene glycol, you get this, put a hat on, do whatever you want right there, as long as it's not acidic condition. Okay, all right. And then deprotection.
Why doesn't the metal particle attack or
This is an ester, it's not aldehyde or ketone. Different functional group. So they have different reactivity. Good question. Okay. All right, that's how we use ethylene glycol. The rest is going to be your practice in this predicting products. Okay, we'll use ethylene glycol much more in synthesis. So basically, like exam 3, next exam 3, you'll see quite a lot of ethylene glycol in there. Okay. All right. Hemiacetal is one halfway. We didn't talk much about it. We just go through it. Okay. Just want to point out something that you'll be familiar with it later. All right. So far we talk about the aldehyde ketone and then all the way to acetal. We just go through hemiacetal. Hemiacetal is not that stable. It's an intermediate. It's difficult to isolate. Once it's made, it just gets used right away. Go forward. Okay. However, there are in nature there are some hemiacetal that's pretty stable. Okay. There are cyclic hemiacetal like that. Okay. Alcohol attack, you get like that's what we call cyclic hemiacetal. And you know this compound pretty well. Do you? What is it? That's glucose. Sucrose, glucose, like an aldose family sugar. Okay. They exist in cyclic hemiacetal. And this is the stable form of glucose, the more stable form. The equilibrium go to the right, this guy right there. You learn that in biochemistry. Okay. All right, let's summarize it. Okay. We have learned a few reactions so far. I mean, they have the same mechanism. All right. All right. You have learned the acetal formation. You can use the ethylene glycol as a protecting group. Yep. You've seen this too. Two alcohols attack carbonyl carbon. Look at similarity. Next reaction. What do you think? What do you think? Same thing. You want to memorize this as a next reaction? Or you want to try to draw the same mechanism? What condition do we run this reaction? Acidic condition. What happened first? Protonation. That's it. What's the proton source in this reaction? Is it sulfuric acid? Is it sulfuric acid? No. Anyone know what does cat mean? Like cat, like cat. It's catalytic amount. How much is catalytic amount? Just a little bit of it, right? You add sulfuric acid to solution, dissociate first. This guy gonna pick up the proton. Can you imagine that? Protonated form of thiol, that's your proton source. Protonated form of alcohol, that's your proton source. Same thing. Not only that, next reaction. Watch closely. Next reaction. Eyes up. 1, 2, and 3. What do you think? Anything familiar? Same thing. Okay. This is the cyclic thioacetal. Thiol is an all term, means sulfur. It's a cyclic acetal, but a sulfur version. Does that make sense? Okay. Same thing with the ethylene glycol protection earlier. Same thing. Now, here's the thing. This guy, cyclic thioacetal, is stable under basic condition and acidic condition. It's on paper, it's a superior protecting group. It is stable in both conditions. The difficult part is to get it off. To remove it, that's the hard part. Okay. All right. To remove it, you can use mercury chloride and water. So just flood them out. Basically, you get that. This is the precipitate out. This is in practice. Okay. Not much of a focus on that. Is it only because of this is in practice? Mercury. Anyone know, is mercury good for you or is toxic? Oh, very toxic. Okay. That's the main reason they don't do this reaction. Because it involves mercury. And you get that. This is the complex with mercury. Mercury have d orbital, blah, blah, blah. I'm going there. I'm not going to get there. Okay. Anyway, if you want to move cyclic thioacetal, that's the reagent. Okay. You can do this too. Hydrogenation with Raney nickel. You don't need to know what Raney nickel is. It's a special type of nickel, like Lindlar's catalyst, similar, something like that. Okay. But when you do that, the cyclic thioacetal remove the whole thing. Oxygen gone too, nothing left. It's a hydrogenation. You have seen this type of reaction before, where you go from ketone to aldehyde and you end up with an alkane. We call that Clemmensen reduction. Remember that? This is the same type. This is the same thing. That's another option you can use. Okay. Later, Maybe today, maybe on tomorrow, you're going to learn this too. We call Wolff-Kishner reduction, similar type. This is later. We'll talk about this later. All right, let's summarize. Okay, there's quite a lot of reaction we can do. Look out. Aldehyde ketone, bam. Do you know the mechanism? Do you know the mechanism? Same thing, either under acidic condition or basic condition. Okay. For cyclic thioacetal, you can remove it using hydrogenation with raney nickel. That's all we have so far. Question on it? That's why I put them to the same group. These are in the same group. See that? Treat them the same way. All right, question. See, this class not that complicated, right? Organic chemistry, yeah, doable. It's just a lot of work. Am I right? Just a lot of work. You got to practice. Okay. Any last minute question? Hey, people on Zoom, are you still alive? They're all dead. Wow. Hey, someone say something. Someone say hi.
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 Okay.
Hi.
Hi. Okay. Miss you. No one say miss you too
I
bad.
miss you
Rude.
too.
Miss you.
Aw.
Miss you.
Oh, okay. Okay. All right. Still alive. Yes. Can you do acetal formation under basic condition? Yes, but the yield is not great. That's why I didn't teach you that. It can, it's just not great. Yep. This is oxygen and sulfur nucleophile. The next part will be nitrogen nucleophile. We got two options. Okay. Look at the differences between these two. For nitrogen nucleophile, you got two types: primary amines or secondary amine. They give you slightly different products. See that? Slightly different. We'll talk about how this different. Okay, and the mechanism. The mechanism is pretty much the same thing. So, all right, let's look at overall first. Let's start with the imine formation. We're using what type of amine? Primary, secondary? Hold on. That is primary, and that is secondary, right? The first one we call imine formation, primary or secondary? Primary, connect to the one carbon chain. Okay, I'll go back one slide. Nitrogen connect to two carbon chain. That's a secondary amine. Okay. Anyway, all right. We saw imine formation first. Okay, so it's a nitrogen nucleophile. The product is imine. Okay, it's a CN double bond. We have seen like carbonyl carbon, CO double bond. Right, so we call carbonyl carbon, carbonyl compounds. This one we call imine. Okay, CN double bond. We name after the inventor Hugo Schiff. That's Schiff. We also call it Schiff base. That's a base. Anyway, it's imine. Okay. Let's see what we add. Instead of alcohol, we add primary amine. Under what condition? Acidic condition. Can you guess what's happening? Okay. All right. There's a slight twist in here, just a little. All right. Imagine this. So let's say you have all this in here, not the product yet, okay? And then you add a catalyst, like let's say sulfuric acid, okay? So you're starting out with the methylamine, a bunch of methylamine, a bunch of them. We use as a solvent to drive equilibrium forward. Remember how to control equilibrium? We use this guy as a solvent, so a lot of them as a solvent. Okay? You're gonna add the benzaldehyde in here. You're gonna add acid in there. All right. Start with an acid. Okay, let's say use sulfuric acid, hydrochloric acid, strong acid. Basically, a few drops of that. Some of this solvent, which is the amines, become protonated. Can you see that though? become pronated. Not all, because we add just like small amount, like catalytic amount. Not all of them. Some of them get pronated. Okay. Equilibrium go forward. Negative 8 here, negative 7 here, 10 there. Totally go forward. So you have some of that in there. So in acetal formation, we use pronated alcohol as a proton source. Are you following on with me on that? In this case, who is your proton source? The pronated amine or ammonium ion right there. That's your proton source. Okay. Now, there's a little bit problem here. The acidity of pronated amines, like ammonium ion, is much less than the pronated alcohol. What's the pK of pronated alcohol? Like hydronium ion? Negative 1.7, a strong acid. Okay, it's strong acid. Now, the ammonium ion is only 10. It's not that acidic. See that? It's not that acidic. So, when we say that the first step is pronation, now take a look. That we're supposed to draw. It's pronation. It's not really acceptable. Here's the reason why. Do you remember how to determine equilibrium? We look at the acid on both sides. Okay, on the left side, that's an acid. That's pK of 10. On the right side, pK about negative 8, negative 7. It goes backward. Can you see that? Pronation first, in this case, is not that acceptable because the ammonium ion is much less acidic than pronated alcohol, like in acetal formation. Okay, so they prefer this on in the mechanism. This is how they propose mechanism. Instead of propose pronation first, they swap pronation. What's happening after pronation? Nucleophilic attack. In amine formation, they swap this two. So they say that, well, this is too slow. Nucleophilic attack happen more quickly. That's why they come up with nucleophilic attack first, which kind of makes sense because nitrogen is much more nucleophilic than oxygen. That's why they do that. Okay. Now and then pronation. The reverse. Does that make sense? Okay. Now this is confusing. I'll tell you this. Listen to me carefully. On exam, you can do pronation first, or you can do nucleophilic attack first. It's up to you. We accept both. What did I just say? We accept both. You can do nucleophilic attack first. You can do a pronation first. I don't really care. It gets you to the same product anyway. Okay? But when they propose in here, they propose nucleophilic attack first. Are we on the same page there? People on Zoom, are you on the same page?
Yes.
Okay.
Yeah.
Yes.
In next 2 weeks, I probably get an email. Hey, should I do nucleophilic attack first or pronation first? Can you imagine people email me like that? There are 400 of you. It's always that guy. They're not even here. So, all right. So we do pronation, nucleophilic attack, pronation. You can swap these two. What's the next step? Guess. Same thing, same core, same 3-core step, depronation. This is halfway done, hemiacetal, but in this case, we call carbinolamine, okay? You don't need to know the name. It's a carbon and amines, that's it. Carbon, carbon, alcohol, amines, carbon, alcohol, amines. Can you see that? Carbinolamine, that's what it's called, okay? All right, next step. So go through the same step, just like acetal formation, okay? What's the next step? Guess. Hey, come on. It's the same cycle. What's the next one? Pronation. Now, who you should pronate? Alcohol or the amines? Alcohol. Okay. Why you want to pronate alcohol? Because alcohol leaves at the end. Can you see that? If you pronate amines, you go backward. It's the same thing. It's fine, but it doesn't get you the product. Anyway, all right, we pronate alcohol. Guess what happened next? Loss of living group. How do I kick out that water? Use the lone pair on the nitrogen. Good job. Kick them out. And then depronation. See that? It's the same step. Same thing. Same cycle. All right. Your turn. Go to the handout. You're going to see this. Same thing. On you, this one. I'm going to keep this up right here so you can compare, contrast. Okay? Can hit this will guide you. Let's go. On exam, if you are dealing with cyclic compounds and when you do reaction with them, I recommend you, highly recommend, put the number on it, on each carbon, so it keep you on track. Does that make sense? You wouldn't lose a carbon, you won't gain the carbon out of nowhere. Okay, put the number on it helps. Okay, it takes longer, but it's just more sure, especially if you like start learning it. All right, so first step is nitrogen attack, nucleophilic attack. Okay, and then pronation. So pronation in this case, look what we use. Since the amines is in the compound, we add a pyridine. Pyridine look like that. This is pyridinium ion, all right? Because the pyridine, that's a sulfuric acid. Pyridine is an amine. Pick up the acid. That's your proton source. Okay, so this guy pick up from the from amine, so new pronation like that. Now you can probably at this point you realize by now there are a lot of pronation step and depronation step. Does that make sense? Okay, as you draw the mechanism more and more, it's just redundant. It just keep very repetitive. Okay, so from exam 3 and beyond, you are allowed to use, write just PT like that. Guess what's the PT stand for? Proton transfer, and just leave it just like that. You're allowed to do that, but make sure you know who's the proton source. Okay, in this case, it's the pronated pyridine or pyridinium ion. This is a proton source. All right, next step right there. You can write proton transfer like that. Remove that one of the hydrogen or nitrogen like that. You can do that too. Okay, but what's the who's the base to pick up one of these two protons though? The pyridine. Pyridine is used as a base. We talked about pyridine before. Remember that aromatic compound? It's available lone pair, localized lone pair. Okay. All right. This halfway down. This carbinolamine. Okay. All right. Next step. So we have to pronate. Who do we have to pronate? The oxygen. We're gonna become water later. So we take the pronated pyridine or pyridinium ion. Pronation, okay, and then loss of leaving group, and pick up the proton, depronation. That's it. Okay, so we call this imine formation. Imines are compounds with CN double bond. Just like that, CN double bond. We call imine. Okay, we use primary amine in an imine formation. There are a bunch of others primary amine as well. So here's an example. Hydroxylamine. This is a primary amine with an alcohol on it. You know, we call hydrazine 2 nitrogen, like 2 primary amine. It's you're making oxy, you're making hydrazone. That's who cares about the name? It's the same mechanism. Okay. Now what? Look down here real quick. When we do use hydrazine, do imine formation, you get hydrazone as a product, CN double bond. It's a type of imine, but 2 nitrogen on it. Something special about this guy. You can do the following. Add a strong base and heat. This guy get removed right away. Because it's Wolff-Kishner reduction. Similar to Clemmensen reduction. That's another way to do it. We'll talk about mechanism in a bit. Okay. Has anyone ever told you to eat a lot of carrots or broccoli? Either you like it or you don't like it. What's the reason? How do they try to convince you to eat carrots and broccoli? Something about your muscle, build muscle? No. What? Your eyes, your good eyesight. Have you ever wondered, is it true? You have bad eyes still? Yeah. So no, you don't believe it. Okay. Is it World War II propaganda? I have no idea, man. So this is why they talk about it. Okay, it's probably propaganda, of course, like an ad the type to put on media, like anything on media. People are like, oh, really? That's true. So cool. Let's talk about that. Okay. All right. People with good eyes, you guys, you see at night, you see like that. Some of you might see like that. You see like that? How old are you? You can look like 16 to me. Are you 16? No? Okay. Okay, 17 is fine. Okay. All right. So this is we call this a night blindness. Usually happen when you get old, you get older. Okay. So old mean like 20. Right? Okay. So what happened is Are you familiar with this compound? Beta carotene. Where do you get beta carotene from? Carrots, anything, any vegetable that you don't want to eat. Okay, so that's where you get it from. Anything that like orange in color, because this guy orange in color. You're taking lab. Have you done the spinach lab yet? Okay, we try to isolate beta carotene. Okay, and lycopene and chlorophyll, whatever. Anyway, all right, this is a beta carotene. Okay, when you eat carrots, broccoli, beta carotene will get cut in half. Okay, this is in liver. You get this guy. We call retinol. That's a vitamin A. Beta carotene is a source of vitamin A. This is not vitamin A, but that's vitamin A. Okay. Watch closely. Look at this alcohol right there. Look at this alcohol. What type of alcohol is this? Primary, secondary, tertiary? Primary. Primary alcohol can be oxidized. How many times total? How many times? 2 total. 2 times. Okay. Either aldehyde or carboxylic acid. Depends on the reagent you use. Am I right? Okay, so this guy can be oxidized by there's a bunch of oxidases. Okay, you can get either carboxylic acid or aldehyde. Exactly what we learned. It's the same functional group. It got the same property. All right. Look at the aldehyde one. Okay, we call this all trans retinal. It's an aldehyde. So we call Al. So all trans. Everything is trans. Alkene is trans. Okay. Now look at right there. We're gonna focus on that double bond in a bit. Okay. This double bond can be isomerized by an enzyme called isomerase, whatever, to get to 11-cis retinal, that guy right there. This is the active vitamin A. What happened to it? When you take vitamin A, you're going to get to this, okay? And look, focus on the aldehyde. That's a protein in your eyes called opsin, right there. This is primary amine. Primary amine can attack aldehyde, forming a compound with CN double bond. What do we call this compound? CN double bond. What do we call this compound? Imine. This is imine formation. Can you see that? This is imine. So we have vitamin A on protein called opsin. The whole thing right here we call rhodopsin. Okay. This protein is pink in color, and Rudolph is like I think it's Greek. It means rose. Like roses, like color, like pink color. Anyway, so that's what we call rhodopsin. When this is in your eyes now, when the light hits, the double bond breaks and it's isomerized to an alkene and the trans version. This change in this isomerization, little change in the molecules like this, it is a signal, and your brain can detect it. Okay, it sends an electrical signal to your brain, and then this is how you see the color. Right? Later, after you see the color, so we have an enzyme convert the trans back to the cis form. And this guy can absorb light again. The more vitamin A you have, the more opsin have vitamin A on it. When they work together, help your eye, how you see at night. Does that make sense? Okay? And if you don't have enough vitamin A, or you have a vitamin A deficient, whatever condition, it's hard to see. That's the only reason. So when they tell you you should eat carrots and broccoli, it help you like see, like have better eyesight. Chemically, it's true. Chemically, it's true. It look like that. Okay. All right. One more thing we have to talk about. So, okay, enamine formation. So this one is secondary amine. Y'all see that? Nope, that's primary amine. That's secondary amine. That's a secondary amine. Okay, this is amine formation. We just learned that. This is what we're gonna learn next. Okay, we call enamine formation. That's an enamine. Let's start with the name first. We call this enamine because it got alkene and amine. That's the name, where the name come from. Secondary amine. Okay, we're gonna compare contrast. I'm gonna put the amine formation mechanism and enamine formation mechanism next to each other and have you compare. Let's start with amine. We do this together. Are you following? We just drew this. This is amine. Primary amine. Attack, you get amine, CN double bond. And here's enamine, secondary amine. Compare, contrast. What do you think? Where is the difference? There's only one difference. Where's the difference? Which step? The last step. Did that? Let me look at the last step. Everything else the same. Can we agree on that? Everything else the same. Just the last step. Let's look at the last step. If you go with amine, making amine, the last step is depronation. What's the purpose of it? To make a neutral compound. Can you see that? However, you cannot do depronation on this guy because it doesn't have that proton. You see that? It does not have that proton. Okay? So, compromise. We use the alpha proton and you get enamine. That's the only reason. Primary amine, secondary amine. Okay? That's pretty much it on the secondary amine. Enamine formation. Okay. All right, we're gonna go back to the reaction that we left off real quick. Okay. Now what? Look at the first step right there. We call this Wolff-Kishner reaction. Look at the first step. Are you familiar with the first step? Look at hard. Look at hard. What reaction is this? This is imine formation. Can you see that? This is primary amine attack. You get that? See, and double bond. This is imine. So we're not gonna talk about the first step. We're done. We're going to focus on the second step right there. Okay. Adding the potassium hydroxide and heat. Okay. We call this Wolff-Kishner reaction. That's a Kishner. I don't have picture of Wolff. This old, very old picture. Can't find it. Anyway. All right. The byproduct. What's the byproduct? I haven't put on here yet. Who leaves? The nitrogen leaves. How many nitrogen? 2. It leaves as nitrogen gas. Okay, if you look at the handout, you have the full mechanism. Am I right? Let me teach you this way. Watch. Okay, this is a skill. If I show you like here's a reaction, predict propose the mechanism. You have to logically propose the mechanism. Here's a logic I'm going to teach you. Okay, now look right here. This is nitrogen, right? What's the bond? Type of bond? Single, double, triple between 2 nitrogen? A triple bond. Okay, a triple bond. Look at before. This is single bond and single bond in hydrazone. Can you see that? At the end, you get a triple bond, right? What reaction makes a pi bond? So one more time. What reaction? Elimination. Going from a single bond to triple bond. How many elimination do you have to do? Guess. 2. We're gonna do 2 elimination. Like E2 basically. To do elimination, you need a strong base. Am I right? Do we add a strong base? Right there. See that? It gotta make sense, man. This is chemistry. It gotta make sense. We add a strong base. And somehow you're gonna form double bond with E2. You do E2 twice. Okay? Let me show you. All right, here we go. The first one. Oh, watch first. This is a strong base. What's the most acidic proton in this structure? On the nitrogen, pK 50 down here, pK 38. Pick that one first. Pronation, depronation, you know? And we're gonna form double bond right there. That's the first elimination. Carbon ion, pick up the proton. Okay? The solvent, the most acidic proton right there. Take water, pick it up. This is the first elimination. You get double bond. That's the first pi bond. If you want another pi bond, one more elimination. All right, we're going to add hydroxide. Where's the most acidic proton? Same thing. The hydrogen right there. See that? We do elimination one more time. Move the electrons. That's a nitrogen gas. This guy, pick up the proton from water. That's it. This is how you guess the reaction. Okay? All right, before we go, do this together. Hold on. Let me do this for you. I'm going to walk you through it. Okay? You might know the mechanism. You might not know the mechanism. It's fine. But put your pen down. Put your pen down. I want 100% in your brain thinking. Okay? Look at the first reaction. I'm going to teach you how to recognize a reaction. There's a lot of reaction you learn today. Yes. But I'm going to teach you, give you some tips. This is how you recognize reaction, especially you never seen this before. Okay? Look at the first reaction. What reaction are we doing? You should recognize this one. This is acetal formation. Now, how do you know this is acetal formation? You see the alcohol? If you remember, how many alcohol molecules can attack carbonyl carbon? 2. Okay? Attack once, you get hemiacetal. This guy, water somehow get kicked out. Another ethanol attack one more time, you end up with that. You don't need to know the full mechanism, but at least you kind of get an idea. That's the intermediate. This is the intermediate that we go through. Does that make sense? Okay, that's something like that. Let's do one more time. Okay, right there, right there. Recognize it. What do you think? Same reaction. Are you following? This is the same reaction. There's a 2 alcohol right there. Can attack that. What do you end up? Can you imagine what you end up? A cyclic. Can you imagine that? Okay, one alcohol attack. That's halfway. That's a halfway. The other alcohol can attack. You end up with that. Look at it like ethylene glycol. This is not ethylene glycol because 3 carbon between 2 oxygen, but it's similar to that. You can use this as a protecting group. Next one down. Nitrogen nucleophile. Nitrogen nucleophile. Look at this one. Primary, secondary amines. Primary, we make an imine, right? This one we make imine. Imine is has a carbon nitrogen double bond. Are you following? Okay. With the first nitrogen attack, can you visualize the intermediate? What's intermediate look like? What's on the intermediate? That will be on intermediate and an oxygen. Are you following? Look like that. Look like that. See that? And then the water will get kicked out. Will kick out as water, right? And then you end up with double bond right there. Right there. That is make sense. Okay, but you gotta recognize the reagent. Okay. All right. Next one down here. What type of amine is this? This is secondary amine. So we're making enamine. You might not know the name. It's fine, but it's not an imine. Does that make sense? The last step is different. Okay. All right. Imagine this first. When the nitrogen attack, can you visualize the intermediate? What's on the intermediate? The whole thing. And the oxygen. When is that attack? You should get that. Can you visualize something like that? This is how you predict the intermediate, which will lead to the product, right? The product, this guy gets kicked out, you get the bond right there, right? And then you get the bond right there, but yeah, you cannot make do depronation to make a single bond. You can't make an imine. This is not an imine. Okay, so we do elimination instead. You get that one. This is enamine. All right, last one. This one you're not familiar with, we just talk about it. Okay, last one. This is the last reaction we learned today. This is Wolff-Kishner reduction. Let me point this out. Everyone look at the first step, please. Look at the first step. What type of amine is that? Primary or secondary? Primary. We're making imine. Are you following? We're making imine. Your imine should look like carbon and nitrogen double bond. Look like that. Am I right? That's an imine. Okay. And the last step is, this is Wolff-Kishner step right here. The second step right there. Nitrogen will leave as a nitrogen gas. The 2 nitrogen right there. Do elimination twice. You end up with just an alkane. Okay. All right. Feel free to copy this. And we're done today. See you tomorrow.